Welcome everybody to the second part of lecture number 5, and in this part we'll be talking about the inductance and the inductors. Of course, all of us know inductance and inductors from circuit perspective. Today we'll talk about those terminology from magnetic field perspective. Before we start, I found it useful to share with you the Greek letters so that you know the symbols and pronunciation of those symbols, because we're going to use them for a couple of lectures. Okay, so now the topic that we're talking about is the inductance. We know the inductance and inductor from circuit theory, but from magnetic field perspective, we would like to introduce the concept. So let us consider the following setup where we have two separate contours or loops, loop 1 and loop 2. Each loop does have its own current, its own contour, and its own area. The current flowing in loop number 1 will produce field B1 everywhere. This field B1 will be linked to the contour of itself and making a flux. And this flux here is denoted by phi 11, which is the linkage of the field generated by circuit 1 over the surface of its own circuit, surface 1. Also, the field B1 generated by circuit 1 will be linked to the surface of circuit 2, and this linkage is called phi 12. It's the flux of field B1 generated by current 1 of circuit 1 over the surface area of circuit number 2, and this is called B12. Of course, increasing current 1 will increase field B1, so that the phi 12 also will increase, and the relationship between I1 and phi 12 is a linear proportional relation, so that we can express the flux linkage between circuit 1 and circuit 2 as a constant called now L12 multiplied by I1. And this constant is the mutual inductance. So the definition of mutual inductance between circuit 1 and circuit 2 is the flux linkage of field B1 generated by current I1 on circuit S2 divided by current I1. This is the mutual linkage of circuit 1 on circuit 2 divided by the current of circuit 1. This is the mutual inductance. If any of the circuits, so let us assume that circuit 2 does have multiple terms. So it's not just like one loop, it's multiple loops. So the linkage will equal those number of loops multiplied by the flux over one loop. That's why is this? Because the flux that goes into one loop will also go to the second loop, to the third loop, so on and so forth. So the flux will go into the circuit number 2 a number of times that is equal to the number of terms in this circuit. So when we have multiple terms in loop number 2, the linkage will be multiplied by those number of terms. So in this case, L12 will equal the total linkage divided by the current of circuit number 1. Okay, so this is the case for linked flux between two circuits, we have similar definition for the self-linkage. So the flux generated by circuit 1 linked to the surface area of circuit 1. And this is called the self-inductance. Its definition equal the flux divided by the current. Again, the flux here, if we have like a number of turns, like if we have N1 turns in circuit 1, so self-inductance will equal the total flux, which is the flux over a loop divided by the number of loops divided by I1. And we'll exercise this more into the examples coming soon. Okay, so we talked now about inductance. Let us talk about inductors. So inductors in general, a coil of conducting wire. It might have like this shape here. We have like a coil winded around a toroid, or a coil rounded around a solenoid core. Usually we have some cores. This core can be plastic, can be foam, can be some magnetic material, and this is called the core. Sometimes also we have no cores. In this case we are saying this is like air core. We have different types of inductors and different usage for those inductors as well. For example, like for audio power supply, the inductors does have iron cores, and for iron cores the inductance is large, but also the the high frequency losses is very high. For very high frequency, or for RF frequency, we are using inductors with ferrite cores. Why? Because as we talked about the material properties, for ferrite material, the permeability mu is high, but the losses, especially at high frequency, is low. That's why for RF circuits, we are using inductors with ferrite cores. Here we have like some different shapes and sizes for inductors, and would like to share with you a number of different names that we have for inductors. Sometimes it is called reactor, especially when we are talking about power grid. Sometimes it is called choke when we're using it for DC current, allowing current at lower frequency, or DC, and blocking higher frequency. We use this name choke, and it is used in RF radio frequency circuitry. We have the name of coil, and in this case the winding is a coil with multiple taps, and also might have like the name of solenoid like this one, and it's used for electromagnet, where we like having the current switching on or switching off the magnet, like for example for relays and stuff like that. So the four names are referring to inductors: reactor, choke, or coil, or solenoid. They are somehow equivalent with different names used in different domains or different industries. So let us now talk about the inductance of a solenoid. As we talked before, the solenoid is sort of like a winding of wires around a core in a straight way. Let us assume that this solenoid is very long, and we are talking about a section of it. So as we studied this problem before, the field inside the solenoid is parallel to the axis of the solenoid. So we would like to know the field be generated by this solenoid. Then we find the linkage of this field with the solenoid. We can go back to the previous lecture, lecture number 4, and find the flux phi1 inside the core of the solenoid. Of course, outside the core of the solenoid, we have zero field. And let us talk now about the linkage for the flux over one term. It's equal to B1.ds. So this is the surface and this is the magnetic field. As I said, the magnetic field is parallel to the axis of the solenoid. We would like to find the linkage of this field with the solenoid terms. So for one term, we have B1 or like BI inside the core dot ds integrating over S1. But as I said, each field is linking itself or like is making flux through all the terms. So the total linkage is n multiplied by phi. So this is the total linkage of the solenoid with itself. From Ampere's law, as we did before, the magnetic field generated by the solenoid equal mu multiplied by Ni, where n is the number of turns per meter, which equals the total number of turns divided by d. And so this is the field in the core of the solenoid. So the linkage, as we did like explained in the previous slide, equal n, the number of turns, multiplied by the flux. The flux in this case equal B multiplied by the area, because we are assuming the field across the core of the solenoid to be uniform. So we have the linkage equal N multiplied by B multiplied by S, where B equal mu Ni over D. So the total linkage equal mu N square Is over D. The inductance, and of course here we have just one circuit, one solenoid, one coil, is the self-inductance equal the linkage divided by I, which equal N square mu S divided by D. And here we are referring to some similarity between the capacitance between parallel plate structure and the inductance of a single turn of the solenoid. So we had assumed that all the field generated by each turn is linking to all other turns. Of course, this is like super simplification of the problem. In reality, the linkage of the field generated by each turn links to one or two like windings next to it, and then we have like this field escaping the solenoid, or we have like the fringing effect. So this is like reality, and this problem is increased, or like this fringing effect is increased, as we said before, when we have like increasing winding pitch, when we are having those winding separated from one another by larger distance. If it is very dense solenoid, we don't have this problem. When we have like less dense solenoid, or like the winding pitch large, we have this fringing effect more. So now let us study the inductance of a toroid. And the toroid does have the cross section of the core. So the core here, if we have like a cross section, if we cut through this toroid, the cross section will be rectangular with height equal h and width equal b minus a. So the field of the toroid, as we like studied before using Ampere's law, we can apply like Ampere's law inside the toroid. It will be like B dot dl equal total current enclosed equal Ni. So if we take like the Ampere's circle or Ampere's contour, like a circle inside the core of the toroid, this circle will be like will enclose all the currents, like will enclose Ni currents as we did before. So the field inside the toroid will equal mu Ni over 2 pi r. So it is depending on the radius. So it is not varying with h, but it is varying with r. So along this area here, which has delta r width and h height, the field is constant. But from this point to this point to this point, we have some variation. So this is the expression of the field. Now we would like to calculate the phi, the flux, magnetic flux over one turn to equal B dot ds. Of course, ds is the cross section as this area, So it's dr multiplied by dz, and we are integrating from r equal a to r equal b, from z equals 0 to z equal h. And of course, as we said, it is uniform along z, so it will be just multiplied by h. Then we have ln b over a. This is the flux over one winding of the toroid. Then the total linkage, we multiply this by n. So we have n phi, and this is the total linkage. We divide by the current. Then we have the inductance of a toroid. So you can use this like result if you need to like wind your own toroid to build an inductance, an inductor. You can use this formula here to calculate the inductance of your coil. Another example here, let us calculate the inductance of a coaxial line. We solved the problem of the coaxial line before, where we have the current in the inner conductor going in one direction, then all this current is returning back on the outer conductor. When we solved this problem before, we had like 4 different regions. Inside conductor 1, between the two conductors, outside inside the conductor 2, and outside the two conductors. When we calculate the inductance, we actually care about only the region between the two conductors. So we need to calculate the field inside this region between the two conductors, then calculate its linkage to this area. Let us see how we're going to do this. So using Ampere's law, because of symmetry in phi and also symmetry in z, if we have like a very long coaxial line, the field between the two conductors in the radius between A and B equal current I over 2 pi rho. So this is the field. Now we would like to calculate the linkage, the flux of this field across this area. So it's B dot ds. ds and B both are in the phi direction. The field expression is here, and ds does have like dr or d rho multiplied by dz in the direction of a phi, and of course we have symmetry in z, so the integration along z will bring d, the integration along rho will bring this ln, and we divide phi by current to come up with the inductance of the coaxial cable. And of course, because it's a very long or like infinitely long coaxial cable, the inductance that we are getting are the inductance per unit meter. So just divide this inductance, or like this linkage, by the length. We will come up with the inductance per unit meter. Now let us talk about a case where we have like two inductors, and let us study this problem where we have two solenoids winded around the same core, but with two different cross sections. So we have like a small solenoid inside a bigger one, and both of them does have the same core. So the field generated by each one of them is parallel to the axis of their common core. So the setup here for coil 2, the field is blue. For coil 1, the field is red. And we would like to calculate the self-inductance and mutual inductance of those two coils. The problem of self-inductance we had solved like in this lecture, and we have this expression for L22 or L11. So this is the self-inductance of coil 1, self-inductance of coil 2, same expression for what we found here in slide number 17. So the new part that we would like to do now is calculate the mutual inductance between coil 1 and coil 2. So this would be the shape. We have like coil 2, like the field from coil 2 is the blue, the field from coil 1 is the red, and we would like to calculate the linkage between those two solenoids. So Bij is the field, magnetic field arising from coil 1 evaluated at coil 2. So this is the one that's used to calculate the flux 12, phi 12. So this is just like describing the sketch with more zoom in. And here we're assuming S2 is smaller than S1. So when we calculate B12, which is the field caused by current 1 at the loops or the core of coil 2. Of course, both of them are on the same axis, and the field generated by 1 equal mu Ni N1 I1 over D. So this is the field generated by current I1. Now we would like to calculate the total linkage to coil 2. So we multiply by N2 the value of phi 12. Phi 12 equals the field B12 divided by the area S2. So this is the total linkage of field generated by current I1 at the area of coil 2. So the mutual inductance equals the total linkage divided by current, which equal N1 N2 mu S2 divided by D. So here, even though the surface area of S2, so the field B1 exists everywhere, but it only link to S2 on the smaller area, just with S2. So those red lines here are not linking to anything. So those are not linking to anything. The linkage is just happening inside. So the linkage, sorry, the cursor was not here. So the linkage is just happening on the area S2, but this lines outside area S2 is not linked to anyone. That's why we are using S2. even though B1 exists on a larger cross section, it is just linking on the smaller area of S2. So M12, the mutual inductance 1,2, does have this expression. Now let us calculate M21, which is the linkage of field caused by inductor 2 linked to inductor 1. So the field caused by N2 does exist only on S2. So there is no field outside S2. The field generated by I2 does have this expression. We see this like a couple of times now. And the linkage to coil 1 equal N1 phi 21. So we have this expression M21. We divide by I2 to get the expression. And we found that the expression of M21 equal M12. And this is one of the properties of mutual inductance. So for mutual inductance, we have reciprocity that M12 will equal M21. So this is the end of part 2 of lecture number 5. Let us have a break and meet again on part 3.